All right, here we are, chapter 9.3, full speed ahead. Hypothesis testing for a population mean when the population standard deviation is unknown, or AKA the t-test. T as in terrific. So this actually, I only assigned two problems from this section, both of which are probably the type of problem you might expect to see on an exam, both word problems. So here's the first one, problem number 15. We have a market research company, and they reported that the average annual earnings of all family practitioners in the United States is $178,000. Oh my, maybe you and I are picking the wrong profession, unless of course you're training to be a family practitioner. Now in Los Angeles, they took a sample of 55 family practitioners and found that, man, it seemed like they're even making more. They're making $192,000 on average, with a standard deviation, I bold-faced it, of 42,387. Do the data provide sufficient evidence to conclude that the mean salary for practitioners is greater than the national average? So again, I bold-faced kind of what we want to zero in on. We think that the average salary for family practitioners in LA is more than the national average. So that's going to guide us in step one, setting up our hypotheses. And technically, like, it's a little bit vague. The book just says standard deviation. So technically we don't know whether it's z-test or a t-test, but we do know from chapter 8 that anytime the book is being vague, anytime the book just says standard deviation and doesn't elaborate as to population versus sample, that it means sample. So anytime I see just standard deviation and I don't see the word population, I don't see that symbol sigma, that's telling me, okay, t-test. So we got to set up our null and alternative hypotheses. Right, the null is that these family practitioners, these doctors in LA, are just making the same as everyone else, kind of the national average of 178. Our alternative hypothesis is that they're making more than the average doctor. They're making more than that 178. And then B and C, to answer those, we're going to need the calculator to get the test statistic and make our conclusion. So again, right, we already observed t-test, so we hit stats because it's stats class. We go over to test because it's useful on a test. We go down, 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 barely downtown to t-test. We fill in the information. Again, look at that. How smart is this calculator? So the calculator knows if we pick t-test, we don't know sigma. So it doesn't ask for it, right? It instead asks for S. S is the symbol for sample standard deviation. We fill all that in. The bottommost line is where we fill in our alternative hypothesis. We already said in a previous slide that the alternative hypothesis is that the mean is more than that mu naught, that 178,000. So here's the information that we're going to need to answer our questions. Our test statistic is 2.46. Our p-value is 0.008, just one bit better than 0.007. And then it says, all right, what's our test statistic? So we already saw it was 2.46. The book also asks, like, what are the degrees of freedom? I think I talk about degrees of freedom a little bit in the narrated PowerPoint. So the formula for degrees of freedom, it's always our sample size minus 1. So if you look back at the previous slides, you'll see that we had a sample of 55 doctors, so 55 minus 1, 54 degrees of freedom. I mean, it's relatively low lifting in terms of something to remember going into a test, but it's extremely unlikely that there'll be a test question asking degrees of freedom. That's just a little too technical for me to kind of spend time testing you on. In general, I try to focus on kind of the big picture problem. So what's our conclusion? Using an alpha of 0.05, we calculated our p-value already. That's 0.008. 0.008 is less than single 0.05. Anytime our p-value is less than alpha, I mean this should be starting to sound old hat to us. Anytime our p-value is less than 0.05, we reject the null hypothesis, right? When the p is low, you reject HO. What does that mean? It means that there is enough evidence to conclude that LA doctors do in fact earn more than the national average. Makes sense. I think the cost of living out there is quite a bit higher. All right, stop the clocks. If you haven't already, pause this and do problem 19 yourself. Solve it, and then watch the remaining slides in a state of jubilant glee as you watch me copy your work and get the exact same answers as you do. So, all right, you've just unpaused it. So the American Community Survey sampled a bunch of people, asked them how long it took them to commute to work. And so the just one way sample mean was 24.5. Here the book actually is explicit. No, I take it back, it's not explicit. It says just a standard deviation of 13.0, but anytime it's not explicit, we know it means sample, so we know t-test. And a transportation engineer claims that the mean commute time for all commuters is less than 25 minutes. So let's test that engineer's claim. So here we're filling in all the information. Again, we're testing less than now, so that last line, we pick the middle option, less than mu naught. There's our test statistic and p-value. So our test statistic is negative 1.69. Our p-value is 0.046, real close to 0.05, but again, technically less than 0.05. We never round our p-values. At least not when doing our comparisons to alpha. So our p-value is 0.046. 0.046 is just a smidge less than 0.05, but it is nonetheless less. Anytime p-value is less than alpha, we reject the null hypothesis, learn it and love it. That means that there is sufficient evidence to conclude the mean commute time is less than 25 minutes. Good job, transportation engineer. Oh, and by the way, good job us.